All right, so molecules. This is going to be the beginning of a long story that we cover together over several weeks. This week, we're going to introduce molecules and how they can pretend to be like ionic compounds, gaining some partial positive and negative charges through electronegativity. But we're going to learn a whole lot more about them when we get to organic chemistry in 2 chapters, and then biochemistry, the chapter after that. So there's a lot to be told about molecules because that's what makes up the living world. Minus the bones that hold those tissues and molecules together. So when we're talking about molecules, we're talking about nonmetals. So we're looking at the upper right side of the periodic table. What's important about this side of the periodic table is the reality is they all want to gain electrons. And if they want to gain electrons, they have no metals to lose electrons so that they can gain. So we have a unique situation. We have no metals, so we have no real strength. We have no ions, so we have no real strength. We just have a bunch of atoms that want to gain electrons, and they are attaching themselves to other atoms that are just gaining electrons as well. So then we have to worry about who gives. And the sense gives here is probably not the best word to use because we want to know who has to share electrons. So what happens with molecules is because they both want to give this octet, or at least achieve this octet of electrons for all atoms except for hydrogen that wants only 2, their ability to share electrons between each other can get them to that magic number. So molecular compounds are things like methane and water. Methane is CH4, H2O obviously being water. What's most important here is carbon has to share electrons with hydrogen. Carbon will receive enough electrons to get its magic 8 to fill its outer shell of electrons and get that magical octet. And the same thing with oxygen. It has 6 electrons. It only needs to share twice, where carbon had 4 electrons, needed to share 4 times. So we can use those predictions to help draw molecules very soon in this chapter. In order to be a molecule, you typically have all nonmetals. So just pay attention to if those are different nonmetals, then we would get into those molecular compounds. Or if we just have the same element with a subscript where we have multiple atoms of the same element, we'd be an elemental substance, both of which categories would apply to the pure substances of our first chapter. There's a funny story about a slide like this. You could tell a joke about it. The joke that I was told when I took chemistry class was that if 2 people walk into the bar, one person orders H2O, and the other person orders H2O2, the other person dies. And the reason for this is adding an extra oxygen makes a big deal. We have a very weak bond between oxygen and oxygen to make peroxide very decomposable. This is why when you pour peroxide into wounds, it tends to bubble and burn, whereas if you pour water into a wound, it doesn't. So the take-home message here is just changing one atom changes a whole lot of properties. And we see that in a lot of the pharmaceutical industry by changing oxygens to nitrogens or removing them altogether to change their polarity just a little bit to change their overall properties as a molecule. So we talked about ionic bonds in a previous video. Ionic bonds were between metal and nonmetal. That's because metals lose electrons and nonmetals gain electrons. Here, though, with covalent bonds, we have all nonmetals. So because both want to gain, they're going to have to share instead. And unfortunately, that sharing is not always perfect, and that's how we get into electronegativity and polarity a little bit later. But if we share electrons, what does that really mean? Well, those electrons can go pretty much wherever they want within the spheres or the dumbbells of those atoms as we talk about electron configuration and the S's and the P's and so forth. What's most important to realize, though, is the attraction of the protons and the electrons allows for them to be within a remedial space in between those atoms most of the time. And that's why we tend to draw a bond kind of connecting those in this kind of central area. So because the electrons can be anywhere, it doesn't help us understand the shapes and the kinds of bonds we're going to see. But just thinking of them being connected where this electron is up here most of the time, this electron's over here most of the time, that's going to give us the best indication of the reality of what ends up being a covalent bond. So even though they can, take turns being on one atom or another, most of the time we're going to draw them as a singular line in between just to illustrate that sharing process between the two nuclei. One thing also we have to make sure we don't take for granted is atoms have a lot of electrons. And the core electrons are the electrons that don't really matter. If you think about it, the core electrons are the ones on the inside. It's kind of like when you walk down a hallway at college or wherever, and you see other people. What you see is what's on the outside. You see their backpack, their clothes, their hairstyle, if they're wearing glasses, if they have a beard, that kind of thing. You can't see on the inside if they're an axe murderer or, a bad person or a good person. You can't see that if they have tumors in their lungs because they smoke or whatever. All you can see is what's on the outside, and that's what we call valence electrons for the atom. So when an atom sees another atom, they see the electrons on the outside. They can't tell if there's 2 or 10 or 18 or 36 electrons underneath. They can only tell if there's 1 or 2 on the outside, maybe 4 or 5 or 6 on the outside if they're getting closer as we move across the periodic table to those noble gases. The easiest way to recognize valence electrons is to look at the Roman numerals. The Roman numerals list themselves 1 all the way over to 8 as we get to the noble gases. Another way to think about it is if you're looking at the numbers 1 through 18, we want to ignore those groups 3 through 12 because those are the transition metals. So even if we look at 1 through 18, if you just look at the ones place, the ones place itself can help us realize that that's really just what the Roman numerals are trying to represent. So as we get to 13, 14, 15, 16, 17, 18, that whole P block over there, what's most important is the 3, the 4, the 5, the 6, the 7, and the magic 8 that all of those atoms want. So pay attention to the ones place, pay attention to the Roman numerals if you have a periodic table that shows Roman numerals, because they're trying to indicate very quickly the electrons on the outside that do almost all the chemistry that we see. So again, in my class, what I prefer to see is to connect the dots. Lots of different teachers teach it a lot of different ways, but I prefer you to connect the dots. So just as we're looking at these examples here, lots of teachers draw them horizontal or vertical. I prefer you just to connect those together. So it's just like you have 1 dot here, 1 dot here, and then you connect them together. This is the covalent bond. And those are the kinds of bonds we're going to start drawing between atoms as we give them a duet of electrons, if it's the case of hydrogen trying to be like helium, or like everybody else trying to be like a noble gas with 8 in that magical octet is trying to be achieved. Another uniqueness about covalent bonds is it always releases energy when bonds are formed. You can imagine that it's kind of like getting married for hopefully the first and the only time. When you get married, you're coming together and you're joining. And as you're joining, that release of happiness, that smile on your face, that first day of being married, should be a good thing. And it's released into the world as happiness. But not all marriages last forever, and unfortunately, you can have outside sources come in and break those apart. So in the real world, if that's money or, children or who knows what, another person, there's always an outside source of energy that tends up to break up that relationship. And that's very similar to what happens in chemistry. You need an outside source in order to separate that happiness, to break up that happiness. So the take-home message here is bond formation always releases energy. It releases that happiness. But just like a window doesn't break itself, if you're going to break a covalent bond, you're going to have to bring in an outside source, a heat source, an electrical source, in order to force those apart, because you're going to take them from something that's noble gas-like back to something that's not. The next thing we're going to look at is thinking about counting electrons, and this is really just looking at the periodic table and understanding that group number is trying to tell you how many electrons to count. So if we're looking at hydrogen atoms, we're really just looking at group 1. It's at the top of the alkali metals. It's obviously not an alkali metal, but it is in the same family in group 1. In group 1, whether you see the 1 or the Roman numeral 1, we know that's just 1 electron. And if 2 atoms have 1 electron, they can share together. And it's most important to realize that what we're sharing here is an unpaired electron. So notice this electron is by itself. This electron is by itself, and those are the ones that we would connect together. So it's very important to notice that we're only connecting unpaired electrons. If electrons are paired up, they're already happy. They're already kind of full in those orbitals. So those are to be left alone, or what we'll call eventually lone pairs. So before we get to too many examples, just remember, if it's hydrogen, it follows the duet rule. The magic number is 2. When hydrogen shares its electron with somebody else, it'll have the magic 2 that it needs, so 1 bond is enough. And then as we look at all the other atoms, just specifically the nonmetals for covalent compounds, what we're looking for is how many electrons does it take to gain, or to share is the better word, to get to that magic number 8. So you can imagine, just based on position, you can probably guess how many electrons are needed. So if you're in this halogen family, you're just gaining 1 electron. If you're in the chalcogen family, you can guess that you're going to be gaining 2 electrons to be like a noble gas. If you move even further over to the pnictogen family, the nitrogen family, so atoms over here are going to have to move over once, twice, 3 times to eventually get to that noble gas kind of octet. And then carbon's going to have its work cut out for them, because carbons are going to have to go all the way back. So 1, 2, 3, and then share 4 times just to get back to that noble gas-like feeling of having 8 electrons. So just the position of the nonmetal can give you a great indication of how many electrons you're going to have to share in order to get to that magic number 8. So when you predict covalent compounds, just pay attention to the Roman numerals, or again, you can pay attention to the ones place of the 1 through 18 numbers. That works too. And then connect the single dots. It's kind of like those kids' coloring books where you connect the dots. It's very similar. Only connect the unpaired electrons, though, if you want to be successful. So as we look at an example with carbon and hydrogen, we realize that carbon has 4 electrons, and the reason that we can say that is because it's in group 14 or Roman numeral 4. So whether you recognize the IV as 4, or when you look at 14 and then you realize the ones place is a 4, either way, that's why they show 4 electrons, 1 on each side. And then when you recognize hydrogen as Roman numeral 1, or when you just recognize it as number 1, you see that it only has 1 electron per atom. And then it's just a matter of connecting them together. So what we want is carbon to have 4 electrons. If it shares with a hydrogen, that's 5, that's 6, that's 7, and eventually that's 8. So when we draw these, what we tend to draw is just these little sticks that represent this sharing of electrons between atoms. So this idea that we can just simplify this and draw it kind of like a 4-way stop, just like a cross, that's what we're after. And it's all based on Roman numerals and group numbers that we can make those determinations very quickly just by looking at the top of their family. So what we see in the periodic table is just recognize the Roman numerals, recognize the ones place if you don't have Roman numerals, and then think about how many connections need to be made. Just realize that fewer connections need to be made as we move closer to the noble gases because we have more electrons. If you're a halogen with 7, you only need to connect once. And that's what they're trying to illustrate here. If you already have 7 and the magic number is 8, that just means connect 1 time. If you have 6, you're going to have 2 connections because 6 and 2 make 8. Just like if you have 5, you're going to have to make 3 connections or 3 covalent bonds in order to make 8. And then if you're in a carbon atom or silicon atom in particular, the ones that we see typically, we don't really deal with germanium in our class much. But if you have only 4 electrons, then you're going to have your work cut out for you because you're going to need 4 more from other exterior atoms. The only exception that we have is hydrogen. If hydrogen has 1, it only needs 1. So pay attention to hydrogen. Pay attention to the halogens also, because they too only have 1 bond. That tells you that these atoms that are kind of in the 4, 5, and 6 families, these guys are going to tend to be your central atoms. And the reason we call you the central atoms here is because they're more than likely to share, more than one time. And that's important because they have those extra electrons that are called lone pairs that will force them to share less and less as we move further and further across those families to eventually a noble gas that doesn't have to share at all. So let's try an example. Carbon and chlorine. So if we go to the periodic table and we look at carbon, we're going to see that it's in group 14. Looking at the ones place or the Roman numeral, we can say if carbon has 4 on the outside, we can put 1 on each side. And then we can go to chlorine and say, well, chlorine is a halogen. Halogens have 7 electrons. So we put a halogen over here, give it 7. Notice I put the single dot towards the middle. That makes it a little bit easier to connect as we start to connect the dots here in a moment. But the reason I'm adding more and more chlorines is I realize that chlorine can only share once, yet carbon wants to share 4 times because it wants 8 also. So once you see as many atoms as you think can make octets, notice by just putting this first one in, that would only give carbon 5 total electrons because it's only sharing 1 with chlorine, but chlorine already has all 8. So this atom's already good on the right side. As we go to the bottom, sharing 1 gives 8 again, but that again only gives carbon in the middle 6, which is not enough. Go ahead and give it another atom with 7, and then that last atom with 8. In each case, chlorine has 8. But now finally, with 4 chlorine atoms, carbon can have its 8 as well. Let's try something very similar down here with phosphorus and hydrogen. So let's think of phosphorus first. Phosphorus is in group 15. So let's put in, based on its one place, 5 electrons. I like to pair up the top just because it looks pretty, it doesn't really matter. And then let's put in some hydrogens. Hydrogens are in group 1. So they're only going to have 1 electron each. And again, I'm aiming those single unpaired electrons towards the middle so that they're easier to connect. And then to make a covalent bond, all we really need to do is connect those single dots only. Notice we left the lone pairs alone. So that's the major difference in what we see drawing those, is just recognizing how many times do we need to share. And if you look at our distance to a noble gas, you can make that prediction pretty quickly. So what we were drawing were called Lewis dot structures. And these Lewis dot structures are just a representation of the valence electrons and the ability to share those valence electrons into more meaningful structures. So as we start drawing more and more Lewis dot structures and then showing these covalent bonds, we'll practice that in a separate video.